All right, so we learned in our previous lessons that resistance is caused by negative electrons colliding with positive ions in the wire. And we saw that if we increase the push from the voltage, unless we have a fixed resistor, if we're using a filament lamp, then the resistance increases as well. What we're going to be looking at today is how resistance changes depending upon the component that you put in. So we had a filament lamp, and we saw that that filament lamp, it had variable resistance, so its resistance would increase and increase, and then it would get to a point where the resistance would get very, very large. When I asked you to use a fixed resistor, you should have just seen a straight line. Now we're going to be looking at what we call VI graphs, and we're going to be looking at different types of resistors. So the first one is an ohmic conductor. So a resistor that has a fixed value that does not depend on the current flowing through the circuit. So this is what they look like in our school, and this is a fixed resistor or an ohmic conductor of 1 ohm, which means no matter what the amount of current flowing through it, pardon me, there will always be 1 ohm of resistance. Remember that we had Ohm's law in the last lesson. The current through an ohmic conductor at a constant temperature is directly proportional to the potential difference across the resistor. If you look at a graph, we call this a VI graph, because remember the symbol for current is I and the symbol for potential difference is V. When we look at a fixed resistor, it is directly proportional. It is a straight line. So if we had, and then this is just going to be very rough, if we had 1 volt, 2 volt, 3 volt, and 4 volt, and if we had 1, 2, 3, 4, 2 and 3, 2 and 4 and 6 and 8 amps, for every increase there would be for every increase in the voltage, there would be a similar increase in the current. Okay, now that is very rough, but it is directly proportional. For every increase in voltage, there is the same step in my current. For every increase in x-axis, there is the same step in y-axis. And a reminder that if I have got 4 volts and I have got negative 4 volts, then they are the same magnitude. When we talk about negative voltage, that doesn't mean that this is 8 times smaller than this. All it means is direction. Okay, so plus 4 volts means the voltage is going in that direction. Negative 4 volts means the voltage is going in that direction. Ohmic conductors will produce a straight line VI graph that goes through the origin. Remember, the origin is 0, 0. So if there is 0 volts, there will always be 0 amps. Non-ohmic conductors means the resistance changes. Now what we see here is that initially there is a sort of a straight line, but eventually that straight line disappears and instead we get this curve at the top. This is a non-linear relationship, a non-directly proportional relationship. What does this actually mean then? If I put some little annotations here, at 1 volt I have a certain increase in the amount of current. So if I increase the voltage by 1, I have a certain increase in current. And this is the increase that I would have for 1 volt. At 2 volts, I have another increase. Now that is not the same as the first step, so it is not proportional. At 3 volts, I have an even smaller increase in current. And at 4 volts, I have a much smaller increase in current. Now, these measurements here, of course, I don't have the measurement of the current, but you can see that the step that we have for 1 is a lot smaller than the step that we have for 2 or 3 or 4. The reason for that is as we increase the current, the temperature, this is an example of a filament lamp. It's the most common one that you give, and a filament lamp will always show this shape because as the current increases, the temperature of the filament increases, and the filament is that very thin wire inside. As electrons flow through it, it starts to radiate energy as light. Now, if we increase the temperature, we increase the resistance of the filament lamp, okay? Because if we increase the temperature, then we increase the kinetic energy of the oscillations, which means we increase the resistance. It's non-ohmic because it doesn't have a straight line. Now, diodes are very special components. You'll have heard of LED before. LED stands for light emitting diode. They allow they allow current to flow in only one direction, and that's why their symbol is this. So my electrons can flow in this direction, and that's okay, but they cannot flow in this direction. And if they do flow, it is a very, very tiny amount of charge. They only allow current to flow in one direction. So over here, I've got in my positive potential difference direction, I have got a flow of current, and it has got very low resistance. And because it's got such low resistance, there is a huge increase in current. But they have a very high resistance in this direction. We can see a very tiny amount of current getting through. They would be microvolts. They would be a very small amount. So diodes, we'll learn about this later, but they can change AC to DC. You might have already done it, but just in case you haven't, don't worry about it. We'll be looking at it later. Diodes have got this particular shape because they only let current flow in one direction. Now, remember I told you that if we increase the temperature, then we increase the kinetic energy, which means we increase the resistance. That is not true for all resistors, because thermistors have got a resistance that changes with temperature. The resistance of a thermistor decreases as the temperature increases, and we can see that in this graph down here. On my y-axis, I've got the resistance in ohms, and on my x-axis, I've got my temperature, being degrees Celsius or degrees Kelvin or whatever. At very cold temperatures, then my resistance is very high. At very warm temperatures, my resistance is very low. Here's how my thermistor would work. If it's cold, then it's got really high resistance, which means my charge cannot travel from one point to another. If you increase the temperature, then the charge can travel. Now, this is a complicated diagram. You do not need to know this, but it's just showing you how we can put a thermistor into a circuit, and it would allow a change in the environment to affect the change in the circuit. Now, current will always flow where there is the smallest amount of resistance. So initially I've got my current flowing through this thing, my preset resistor, but if I increase the temperature on this thermistor, then my current is going to stop flowing in that direction, and instead it's going to flow in this direction, causing my LED to light up. We can use thermistors in thermostats to control temperature in the home. Anything that, or even if you've used a hairdryer and you've used it for too long, sometimes it just shuts off. Or any kind of a heater. That's because it's getting to unsafe levels, and it's probably because of a thermistor, of a heating effect in the thermistor. Now, it's really important that you remember what this graph looks like, because you could be asked to sketch it. So cold at the origin, and then hot up here later on, and it's this sloping shape. Now, I mentioned diodes, LDRs, LEDs. That is not to be confused with light-dependent resistors. LDRs are types of resistors where the resistance varies with light intensity. The resistance of an LDR decreases as light intensity increases. So if in the same rough shape as my thermistor, where my resistance decreases as my temperature increases, in my LDR, my resistance decreases as my light intensity increases. So when we're dark, we've got a really high resistance, and then when it's got lots of light, we've got a really low resistance. You can see that here. My charge cannot get through until the light shines on the top of my LDR, allowing my charge to go through. And the same thing in this diagram. You do not need to understand this, so do not worry. But it just shows that there is an ability for my LDR to change the direction of charge. LDRs are used as switches to turn on street lights when it gets dark. There's not someone at Hull City Council who flick on the street lights at night time. It's just that when the light levels get low enough, and when the light levels get low enough, then my circuit switches on. Okay, that's that.